Good morning, class, and welcome to this lesson on Newton's third law. Today we are going to be able to define Newton's third law, so we have to look at that first, and apply that to an interaction of two or more objects. So Newton's third law and an interaction between two or more objects. This is going to be a completely conceptual lesson, no math involved here today. But we will later use a lot of problems applying this law. So let's first look at what an interaction is. An interaction is a force. Excuse me. A force is always part of a mutual action that involves another force. So a force is always part of a mutual action that involves another force. That is an interaction of two objects. Okay. So when two objects interact, we call that an interaction pair or an action-reaction combo. And so, to give you a very basic example, this is my book demo. I have this awesome book right here. I think many of you love it. And so if I take this book and I push on it, and I'm pushing on it with 2 newtons, the book is pushing back with 2 newtons. So if I push this way with 2 newtons, there's going to be an equal and there's going to be a reaction going in the opposite way. So that is an interaction of forces. There's always, if I push this way, the book pushes back the other way. And this is where we get Newton's third law. So let's define that. Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So, you may have heard this summarized as for every action there is an equal and opposite reaction, and that is Newton's third law. That is also applicable. So whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. That's why I said with my book, if I push with 2 newtons this way, it's going to be equal and opposite the other way. So that was the book demo. There's also, another demo would be tug of war. Tug of war. If 2 people or 2 teams are doing tug of war, which team exerts a greater force? Which team exerts a greater force? And the answer to this question is they both exert the same force. Because however either one of those people pull, those teams pull, there's always going to be an equal and opposite force applied. And then you say, well, that doesn't make any sense. How can one team possibly win if they're both pulling equally? And the reality of this is whichever team has more friction. So if this team has more friction, they're both pulling with equal and opposite forces. This team has less friction. They're going to end up being pulled over to the right. So both teams pull with equal and opposite forces. Just one team has more friction to keep from being pulled over the line. So that was tug of war. So I just want to look at a few very basic action-reaction combos. And this is going to kind of change the way you look at things in life. At least I hope it does. These are some classic action-reaction combos in physics. And so these are also known as interactions. So first thing. Do you propel yourself forward when you run? So let's look at running. Do you propel yourself forward when you run? Do you force yourself forward? And the reality is no, you don't. When you run, you push the ground backwards, and because there is an equal and opposite reaction, the ground pushes you forward. So you push backwards, there's friction there, so your foot doesn't slip, hopefully. You push the ground backwards, the ground pushes you forward. Same thing with swimming. Do you force yourself forward? And the reality is no, you don't. You force the water backwards. and then the water has an equal and opposite reaction, and so then the water pushes you forward. So the harder you push backwards, the harder the water pushes you forward. So the harder, if you can push backwards harder, you will therefore swim faster if you have good technique, that is. Let's look at a rocket. A rocket. How does a rocket move? Well, a rocket pushes gas backward out off its tail end, and then the gas pushes the rocket forward. This is how rockets can fly in space. Because if you think about it, there's no air in space. Just like if you're running, you push on the ground pushes you forward. You have a medium to work off of, right? And you think, but in space, there is no medium out there. There is no air, there is no ground. How does the rocket push itself forward? Well, it creates its own gas through the chemical reactions of the engine. It pushes the gas backward, and then the gas pushes it forward. So, an apple in the earth. An apple in the earth. What pulls harder? What pulls more? What has a greater force? The apple on the earth or the earth on the apple? And the reality is they are the same. They are the same. The earth pulls on the apple just as much as the apple pulls on the earth. So, apple pulls on earth is equal and opposite to the earth pulling on the apple. Okay? And my last one and most favorite action and reaction is the dog and its tail. Does the dog wag its tail? You can say yes. But that also means there is an equal and opposite reaction. So the dog wags its tail, and then, because there's always an equal and opposite reaction, the tail also wags the dog. For every action, there is an equal and opposite reaction. Action-reaction combos. Now, you may be looking at some of these, especially this like apple and earth situation, and saying, that doesn't make any sense. The earth pulls the apple down. That apple, when I throw the apple up, the earth doesn't go accelerating up to the apple. But let's take a look. Let's take a look. I'm going to draw an apple. This is apple and earth. And what we're saying here is the force in between these is the same. That's an equal sign. Maybe I should. So the force is the same between these two things. So F equals, I'm going to do little m, big A, and I'm going to do F equals big M, little a. So you were thinking, why'd you draw that? What's up with that? So we have our equation, F equals ma, Newton's second law. And what this is really saying is, okay, the force between the apple and the earth is the same. But because the apple has so the force, these two numbers are the same. Because the apple has such a little mass, for this number to be the same, the acceleration must be a lot greater. That's why we see an apple accelerating towards the earth very, very quickly. So let's just say, for example, to make it easy, the force is 10 newtons. And that means, and we're going to call the mass of the apple 1 kilogram. That must mean the acceleration is 10 meters per second squared. Okay, just to make it simple. Okay, this is obviously way off in numbers. Okay, so that's what I'm trying to say. The force is 10 newtons. 1 kilogram object is going to accelerate at 10 meters per second squared. Let's do the same thing now. The force is 10 newtons, but let's say the mass is 10 kilograms. What's the acceleration going to be? It's going to be 1 meter per second squared. So when an apple has its own gravity, just like everything has its own gravity, so the apple does pull up on the earth. But because the earth is so very, very, very large, it's going to have a very, very, very small acceleration. It's going to move very, very slowly. And because the apple has a very, very small mass, it's going to have a very large acceleration, so it's going to move very quickly. So what we see is the movement of the apple. We see the acceleration. But for some reason we think that is force. So here is a hint. It is, or a tip. I guess we would call that a tip. It is easy to confuse force for acceleration. They are related. I mean, we have the equation, F equals ma. They are related, but they're not the same. I'm going to do one more example. Okay? Big car, small car. Big car, small car. So we have two cars and they get into an accident. And the question is, which car applies more force? Which car applies more force? And the reality here is they both apply the same force because there's an equal and opposite reaction. But you're thinking, no, no, no. I know for a fact, common sense tells me that I want to be in the big car. Because if I'm in a big car, a big old truck or whatever, I know that there's going to be less damage, and I know that it will hurt less. And the reality is that's true. Because when you are in a big car, you have a big mass, and so you're going to have a smaller acceleration. And if you're in a smaller car, you have a smaller mass, and you're going to have a bigger acceleration. And so when you get into a car accident, your body accelerates or decelerates. And so when you get injured, when there's whiplash or anything else like that, what you're really feeling is you're feeling acceleration. When you have a very large acceleration, that hurts. Okay? We don't want to have a large acceleration. If we accelerate very, very quickly, that means our body's whipping around. It's stopping very quickly. That's painful. And if we have a small acceleration, that's better. And that's how they try to design cars. They try to design them with a smaller acceleration when they crash, with crumple zones and things like that. I'm not going to get into that right now. So the reality is, between a big car and a small car, the force is equal. But because the car is bigger, F equals ma, it's going to have a smaller acceleration. And because the car is smaller, it's going to have a larger acceleration. It's easy to confuse force for acceleration. Remember, all forces, if there's an there's an action-reaction, all forces are equal. So that concludes my lesson on Newton's third law.